Welcome back, students. Today we're going to take a look at one of the most studied problems in graph theory, and this is known as the traveling salesperson problem. All right, so the name of it suggests that it's going to be a fairly easy problem to solve. All right, traveling salesperson. So you're thinking about somebody that lives at home, they go out and visit other houses to try to sell things, or maybe they go to different companies, whatever the problem may be. But what it is you have somebody that starts off at home, they leave, they go out to try to sell something, and then of course they have to return back home. All right, so the description of it is basically right there in the name, traveling salesperson problem, or sometimes shortened to be TSP. But it actually is a very complex problem to solve. It's been studied for years, and the best solution is still out there. All right, so we do have some ways to solve it. However, the best solution is still to come. All right, so the scenario that I described is actually a Hamiltonian circuit. Okay, why is it a Hamiltonian circuit? Well, because you have the salesperson that's starting off at their house. They're leaving to go visit other vertices. Okay, they will take an edge to go from a vertex to the next vertex. However, they only need to use one edge. If there are multiple edges, they don't have to use all of them. They only have to find one edge going from one vertex to the next. Okay, and then after they've gone out and sold whatever they need to sell, they're going to go back home. All right, so that means that they are going to start and end in the same place. So this is describing a Hamiltonian circuit where you are going to start off with a vertex, you're going to use an edge to get to the next vertex, you're going to go to all of the vertices, and then you're going to end back where you started. Now, these graphs are going to be weighted graphs. Okay, why are they weighted graphs? Well, because there are going to be numbers next to each edge. These numbers are going to usually represent distance, cost, or time. And so with the TSP problem, you're trying to figure out what is going to be the shortest Hamiltonian circuit, right? What is going to be that minimal Hamiltonian circuit? And the way that we can solve these, okay, the two methods that we're going to study are called the brute force method and the nearest neighbor algorithm. All right, so right now, the brute force method, this is going to guarantee the best route every time. It's going to give you the optimal meaning the best solution every time. Now, the reason why it's not necessarily the best method to use is because it's going to be very time consuming, especially when you get a larger graph. Now, computer scientists are able to program computers, but it will still take computers a long time to figure out this best method or this best route. The way that you do the brute force method is you will actually list out every possible circuit that there is. You're going to add all of the weight together, and you're going to then figure out what is the circuit of the least weight. Okay. So it's going to produce the optimal solution every time, but not necessarily is it the best method because it is so time consuming. So computer scientists have come up with another method, and that's called the nearest neighbor algorithm. Now, this is going to be a much faster process. However, it's a heuristic method. Okay, right here, that vocab word, heuristic method, because it's going to be a quick and reasonable answer. However, it's not necessarily the optimal solution. It's going to be close to the optimal solution, but it's not necessarily going to be the lowest or the circuit with the smallest value. It's going to be close to being small. Okay, it's going to be close to being the smallest, but it's not necessarily going to be the best solution. And so the way that the nearest neighbor algorithm works is you're going to start off at your home vertex. All right, so wherever you're told to start, you're then going to go to the next vertex. And instead of choosing any route to take, you're going to take the smallest edge. So you're going to take the edge of the smallest weight, and then you're going to continue to do so, going to each vertex that you have not yet been to until there are no other vertices that you haven't yet been to, and then finally you're of course going to go back home. All right, so those are going to be our two methods. Okay, the best method is actually still to come. Okay, that's why this problem is still being studied. And if you win it, or if you actually come up with a better method, you're probably going to win a Nobel Prize for doing so. All right, so we're going to take a look at one example. And here we have our graph, and we're going to pretend that we live in St. Louis and that we are a salesperson, and every week we need to go to Minneapolis, Chicago, and New Orleans for work. Now, obviously, we're going to start off at St. Louis, and that means that at the end of the work week, we are going to want to return to our home in St. Louis. It tells us to find the least expensive route to take. Okay, so that's important. Okay, it's telling me that these weights on this graph, okay, these numbers are telling me not the distance, they are telling me the cost to travel from one city to the next. All right, so let's do the faster method first, the nearest neighbor algorithm. All right, so what I'm going to do is I'm going to start off where I'm starting, which my home is in St. Louis, so I'm going to go ahead and list that first. So starting off here in St. Louis, and then I need to look to see where can I travel to. So it's adjacent to Minneapolis, Chicago, and New Orleans. All right, big city, of course, I'd be able to travel to all of these other big cities. But what I want to do is I want to look at the edge that is the smallest weight. So 550, 270, 670, obviously traveling to Chicago. From St. Louis to Chicago, that's the cheapest route, so that's where I'm going to start off with. So down here where I'm listing where I'm going, I started with St. Louis, and then next, because it is the smallest weight, I'm going to go to Chicago. And then from there, okay, so it's probably a good idea to mark off where we've been. All right, so this is our home. So I'm going to put an H for home, and now we're going to go to Chicago. All right, so now we've been to Chicago. So now we have to either go to Minneapolis or New Orleans. All right, so from Chicago, Minneapolis, weight of 400 or weight of 910, we choose the smallest. So that means we're going to go to Minneapolis next. All right, so now we've been to Minneapolis. Our vertices, we only have one other vertex that we haven't been to yet. So it doesn't matter what the weight of this edge is, we have to take. And if there was multiple edges, then we could choose from there. But it looks like there's only one edge to go from Minneapolis to New Orleans. So we're going to use that. And now we're going to go and visit New Orleans. So we're going to add it to our circuit. And so then finally, now that we've been to all of the cities that we need to go to, now the end of the work week, we need to go home. All right, so here's our circuit. We start with St. Louis, we go to Chicago, we go to Minneapolis, we go to New Orleans, and then we go back home. All right, so there's the Hamiltonian circuit. Now what we're going to do is we're going to add up each of the edges and figure out what is the total weight of this circuit. All right, so I just list the weights here, and there were 1, 2, 3, 4 edges that were being used. So I have my 4 weights. I'm going to add all those together, and this gives me 2,600. Which means that this total cost was $2,600 to go and visit each of these cities and then go back home at the end of the work week. All right, so this is going to be possibly the best solution. Okay, the nearest neighbor method could produce the optimal solution. However, it might not be the lowest figure that we have. No matter what, it's going to be close to the lowest figure, and that was a very painless method for me to use there. That was very fast and pretty easy for me to do. All right, so that is a very good solution. However, it might not be the optimal, might not be the lowest figure that we have. So now we're going to use the brute force method, and we are going to list every possible circuit that there is. We're going to figure out what's the total weight for each of those circuits, and then we're going to just choose the one that is the lowest. All right, so here we go. What I'm going to suggest that you do is make a tree. You don't have to make a tree, all right? But usually making a tree is going to guarantee that you're not going to miss any circuits. If you don't make the tree, you might miss a possible circuit. So I'm going to make a tree diagram. All right, so how I would start to make that is we're starting at St. Louis. All right, so this doesn't represent S for start, but it's kind of nice that it does represent start, but it really is representing in my problem St. Louis. And then from St. Louis, I'm going to list any vertex that it's adjacent to. So it's adjacent to Minneapolis, it's adjacent to Chicago, and it's adjacent to New Orleans. So now I would list those out. All right, and it's a tree diagram. So it's saying we could go to there, we could go to there, we could go to there. And then it'd be a good idea to list what the weight of each of these edges is. So this one, the weight was 550. This one, the weight was 270. And this one, the weight is 670. All right, and then what you do is from Minneapolis, All right, from Minneapolis, what's a vertex that you haven't yet been to? So from Minneapolis, you could go to Chicago, or from Minneapolis, you could go to New Orleans. Okay, and then if you're going on this route, Minneapolis, Chicago, the only other one you haven't been to yet is New Orleans. And then don't forget you have to go back home. So you'd also need to put going back to St. Louis. All right, this one, St. Louis, Minneapolis, New Orleans, Chicago, and then back home, and so on. All right, so I'm going to go ahead and put my completed tree diagram in here now. All right, so here is my completed tree diagram. All right, it gives me all of my possible cases, all of my possible Hamiltonian circuits. All right, so notice that there are 1, 2, 3, 4, 5, 6 possible circuits out there. So it's kind of time consuming. Imagine if I added more vertices, it'd be even more time consuming. All right, and then once I listed all of these possible circuits, these numbers at the bottom are just the total weights for those circuits. So we have 2,530, 2,990, 2,600, and then 2,990 again, 2,600, 2,530. All right, so we should notice two things from this. One thing is we now have a new low number. All right, so we now have a new low cost. Okay, and this is going to tell us what our optimal solution is. But not only do we have it once, we have it twice. So let me go ahead and list out those circuits. All right, so those two circuits of lowest weight, of lowest cost, it was going from St. Louis to Minneapolis to Chicago to New Orleans to St. Louis. And the other one was going St. Louis to New Orleans to Chicago to Minneapolis to St. Louis. Hopefully you see St. Louis, Minneapolis, Chicago, New Orleans, St. Louis, Minneapolis, Chicago. It's just the same circuit. It's just backwards. All right, so what that means is the brute force method, while a tree diagram does take a while to make, okay, there is a way for us to make it a little bit smaller, and the fact that these circuits are the same as these, they're just backwards. So you don't need to make a full tree diagram. Instead, you only have to make half the tree. All right, so there it is. That is your traveling salesperson problem. You have two methods, the nearest neighbor algorithm, okay, which gives you a close to optimal solution. Sometimes the optimal solution, it's fast and it's easy, again, but it's not always optimal. The brute force method always gives you the optimal solution, but you got to make a tree diagram. You got to list out all possible circuits. So it's time consuming, but it will give you your optimal solution every time. Again, if you're going to go into the field of computer science, you might study this problem and maybe you'll come up with a better method and win the Nobel Prize. If you do, remember, Mrs. Riddell was your finite teacher and was the first one to introduce you to this problem.